Something, or can I start? I can start. Okay, so welcome back, everyone. Oops, sorry. First of all, this morning I didn't have time to see who volunteered for the notes. You don't have to raise your hand now, but if you could stay here after the lecture, so we could just group, talk a little bit together, that would be great. All right, so shall we start? So this is where we stopped, pretty much. We were talking about how clouds are coupled to this circulation, and I hope that I've convinced you that clouds are associated with upward motion. And I've had some interesting discussions over lunch about the fact that clouds are the result of the upward motion, or they are the cause of the upward motion. And as mentioned this morning, correlation does not imply causality. It's hard to know in observations what causes what. We can just look at correlations and then use simple models or simulations to answer the causality question. But as far as this descriptive part is concerned, we have, I think, seen that upward motion is associated with cloudiness. And so we've looked at the planetary scale circulation, and we started talking about the synoptic scale. In fact, we were almost done. We saw this really nice example of a place where the theory was verified in observations with the caveat that you had this little blob that was not expected, the MGO. And whenever there's something that surprises you, it's usually something that's going to make researchers very happy, because that means that you're surprised by what you're looking at, and there's probably something interesting to look into. And in fact, there has been quite a lot of research on MGO since then. And then we looked at these Hofmüller diagrams of OLR anomalies, where we noticed all the different equatorial waves. So you had the fast Kelvin waves, the equatorial Rossby waves, the large scale, slower motion of the MJO. And then someone noticed that you had those little small pulsation of cloudiness, which looked organized at somewhere in the mesoscales, hundreds of kilometers. And indeed, these are mesoscale convective systems. And the way they organize is still somewhat mysterious and is something that's currently actively researched. And so we'll see more about this in lecture 3. So that was for the tropics. For the exotropics, we also saw that the clouds are embedded in the frontal systems. And we saw this map earlier of the various things that we can see from satellite, infrared, water vapor, and visible. And what I hadn't shown you is the temperature field that corresponds to this map. And there's a couple things that, well, what do you see? Yeah, you see a sharp gradient, especially here. And this is a cold front moving. And as mentioned briefly this morning, the cold fronts tend to be abrupt, quite vertical, more slanted than the warm front, and associated with more extreme weather. So you have a strong cold front here, and in fact you do see the warm front, but it's a little more blurry. And this is a schematic of what's going on and how the clouds are embedded. And so here you have the cold front, and you have a very sharp limit of cloudiness just in front of the cold front. Yeah. Oh, that's a very good question. Okay, so in terms of the schematic, the cold front is represented as a blue line, and the triangles will point toward the direction of propagation. The cold front is a mass of cold air advancing through warmer air. Okay. A warm front is represented as the red line with those semicircles, and that corresponds to warm air advancing into colder air. And that's very typical of mid-latitude weather patterns, where you have the high and low pressure systems embedded within the jet stream. And associated with those cold and warm fronts, you have cloud cover, so very steep clouds where the cold fronts are, very vertical. And again, the slope is steeper for a cold front. The warm front also is associated with cloudiness, because you're raising, again, it's associated with upward motion, so you're raising air above the cold air, you're raising the air, which tends to lead to condensation and cloud formation. More spread out, a little more blur. Okay. So that's it for the first lecture. Any questions so far? No? So the idea was to describe what's going on. Again, these are objects that we see every day, so we have some intuition about clouds. I hope that now you have a better idea of what's the cloud cover, the different cloud types, where we find them. And obviously the question is, why are the clouds distributed the way they are? And so in order to answer the question, we're going to have to go into more details about cloud physics. I have to tell you a little bit about thermodynamics. So David has done some of the work this morning. But since you only saw them this morning, I will recall some of the main results that I'll use. Okay, cloud formation and cloud physics. And so as I said, we'll start by some thermodynamics on cloud formation, discussion of the instabilities that lead to this upward motion and this convection. And then we'll describe what's the life cycle of an individual cloud in contrast with organized clouds. So here we're concerned with the phenomena, the processes that are going on in the different types of clouds. Okay? Okay, so again, this wonderful animation that, as you've seen, I really like, of cloud formation. And in terms of the instability, so we want to understand how clouds form, and so they tend to be associated with upward motion. Okay, so we'll start with a simpler question, which is, when is a dry atmosphere unstable to convection? Okay, and again, this is motivated by what we see, our intuition that clouds are associated with convective motion, upward convective motion. Okay, so let's ask this question. When is an atmosphere unstable? So you've all been hopefully hiking this afternoon, and you've seen that the higher you go, the colder it is, right? So you have colder air aloft. But that doesn't mean that the air is heavier. Otherwise, the whole upper atmosphere should fall on us. So why isn't it so? Well, if you want to know if air is heavier or lighter, it's not the temperature that you have to compare, but the density. And one thing that makes our lives miserable is one way to put it, or interesting is another way to put it, more optimistic, is that the density is not only a function of temperature, it's a function of pressure. Okay? And so it obviously makes things more complicated or more interesting. So we can't compare air, which is near the surface, to air which is higher up, because yeah, they have different temperatures, but they have different pressures as well. And so to compute their density, we need to account for this pressure change. So how are we going to do that? I'm going to need the first law. And so David gave you the main results this morning, but again, as you only saw them this morning, I'd like to give you, to refresh maybe your memory a little bit. Also, I have a different approach. I actually like to start with the momentum equations, and from them derive the energy conservation equations. So, okay, so what I'm going to do is take a parcel of air. This is called the Parcel Method. It's a classical method in atmospheric science. You take a parcel. If you want to know if the atmosphere is stable or unstable, you take a parcel, you raise it adiabatically, so without any heat import or export. You raise it, and then you see whether it's more heavy than the environment, and it goes back down. It's stable. Actually, it oscillates if it's stably stratified. Or you can take your parcel, raise it, and then see whether it's lighter than the environment, in which case it keeps rising. Okay, and that's the definition of an unstable atmosphere. Does that make sense? Yes? Okay, so it's called the Parcel Method. And obviously the thing is, I need to know how its temperature changes as it raises adiabatically just from pressure forces, pressure force work. Okay, so I need the first law. So let me back up a little bit, and I'm going to take this parcel, And let's say that I have molecules in them. So each molecule I has mass mi, say, and a speed, I think, I'm going to use the same notations as David, so ui. Yeah, sure, of course. Yeah, that would be better. I agree. Last one. Better? Thank you. Okay, so each molecule has a certain mass mi, a certain velocity ui, which I am going to decompose into the velocity of the center of mass plus a perturbation. Okay, so u is the velocity of the center of mass, which is the sum mass weighted average of velocities, so sum of mi ui over the sum of mi. Okay, and so the way you derive the equations is actually you would write the momentum equation for each single molecule, and then you add them all, and before that you multiply by the velocity to get the energy equation. Okay, maybe I should write this down. So you can write, yeah? Yes. Yes. And the mhm. I know. So here's the thing. When this morning you wrote the equations, you had let's say the macroscopic kinetic energy. So you had d dt of u squared over 2 plus the potential energy, again macroscopic, is equal to the work, the large-scale pressure gradient, right? And then you had the microscopic, I would call, energy equation. I should say energy equation, which is also the first law of thermodynamics. Which tells you that d dt of the internal energy, CVT, is equal to the rate of heat added to your system, and then you had a minus 1 over rho p dvu. And this is nothing, actually, but the change in specific volume alpha. Okay, so this is the first law. This is the work of pressure forces. If you've never seen alpha, this is specific volume, so 1 over rho, volume over the mass, the total mass. So here, actually, what you're looking at is the temperature is nothing but the kinetic energy of those perturbation. It's proportional to the sum of the kinetic energy of those perturbation. So actually, to derive the first law, you need to write the momentum equation conservation for each molecule, and then you can separate into a mean and a perturbation, and then you get those two equations that he derived this morning. Yeah. But it's not the Navier-Stokes equations because they do interact. So you have interaction terms, which I'm happily hiding in here and in here. Okay, so it's a little more involved, but all right, so let me write that down clearly. So you write momentum equations for each molecule. And indeed, you have to account for the interaction between the molecules, the exchange of momentum through collisions. And I'll refer you to, so you saw it in David's lecture this morning a little bit. And so the book that I mentioned this morning, Boron and Albrecht, has a full derivation. And so when you do that, indeed, you find, I'm going to repeat the equation, you found what you saw this morning, the macroscopic equation, which I'm not so much interested in here. Okay, so this is the kinetic energy, which is associated with the motion of the center of mass. And again, so what I'm interested in these lectures is not so much into the mathematical details, but it's trying to give you some intuition of what's going on and where the terms come from. Okay, so I'm not going to derive this in detail. You can find them in books, and we can discuss this in at any moment you want outside of the lectures. But I want to motivate where these come from physically. Okay, intuitively, where do these come from? And we'll think about actually places where those things break down. And I think that helps you build intuition on those various terms. Okay, so this is the kinetic energy associated with the motion of the center of mass. Okay, oops, sorry. This is the potential energy, and this is the large-scale pressure gradient. This is the macroscopic part. What I'm interested in is more the microscopic or the thermodynamical part. And so indeed, you have that d dt of the internal energy CVT is equal to, and then dq dt is, as someone noticed, there's interaction between particles and with the boundaries. And so all these intermolecular forces are hidden in there. So it's the amount of heat that you're adding to your, so okay, I should say this is the kinetic energy associated with motion around the center of mass. This is the motion that, yeah. Yeah. Here? So here, so it depends. This is the rate of change with time. So this is the rate of heat added to your system. And then depending on your units, you can define Q as the heat, the specific heat added. Depends if it's per mass or not. Here, this is all per mass. This is all, remember from this morning, specific, I can write it, this is the specific volume. Specific means per unit mass. I've been asked a couple times, why does specific refer to per unit mass? Doesn't make much sense, does it? I don't know, but it's the jargon, so I'm sorry I have to stick to it. So this is the specific volume per unit mass. Similarly, this is the specific heat capacity at constant volume. Okay, so this is all per unit mass, understood. And again, I'm more interested in building the intuition than in the details, but I hope that answers your question. Oh, so there are two ways to write the ideal. So let me write the ideal gas law in two ways. Minus P d alpha. So you can write, now I can erase this. Okay. So there's a few things I haven't showed. The first thing is I told you that this term, actually this morning, what's that? Yeah. Okay, to answer your question, the first law is sometimes written as d of internal energy equals some infinitesimal heat input plus infinitesimal work done on the parcel. Okay, so this is heat added to the volume or the parcel, and this is work done on the parcel, and in specific notation, so per unit mass, it's minus PD alpha. You may be used to seeing minus PdV. So if you translate per unit mass, you get minus PD alpha. So maybe that's the way it was written this morning. I think he used both. But typically in thermodynamics, we write things like this, just because we don't like to have dTs everywhere. But intuitively, physically, where these come from, they come from experiments that were done in labs where people were measuring the change with respect to time. So whenever we have a d something, physically what it means is that a rate of change per unit time. Okay, but this is a shortcut notation for that. Okay, does that make sense? And one thing that I haven't proven from this morning is that what you had here was not minus p d alpha. Do you remember what you had? Yeah. That's how it was this morning, so I have to show you. It's going to be, it's not very hard. Let's show that, so rho d alpha dt is equal to d view. And I think actually they mentioned this morning that d view is nothing more than the change of volume. So it's true. Let's show it. Can I erase this? First, is that clear for everyone, where that comes from? Yeah? Okay. Has to be clear now because I'm going to use the first law. So I'm assuming that now you are all at least comfortable with where it comes from. The fact that it's the motion, sometimes called the motion that does not go anywhere. It's the motion that's useless. It's just moving around the center of mass. Okay. So actually, who had seen the first law, at least in this form? Oh, okay. Oh, maybe you didn't need this lecture. Okay, good. Okay, so let's show this mainly mathematical. So we said alpha is it's the specific volume, so it's 1 over rho. And so, yeah, so rho d alpha dt is rho d1 over rho, so that's minus d rho over rho dt, right? So that's minus 1 over rho d rho. And then you saw the density equation this morning. Do you remember what that is? Yes, minus rho d view. Okay, so that was not too long. Okay. All happy with the first law? Yeah? Okay, so let's raise our parcel. Again, adiabatically. Can I turn off the light? Yeah? Okay. Maybe I'll just put a little bit of light so you don't fall asleep. Okay, so let's start our parcel and raise it. And again, the question is, does it become unstable or not? And it will be useful to see that there is a conserved quantity. That's the last thing that you saw this morning, potential temperature. And it's easy to show. So again, we start with the first law of thermodynamics. And now we all know that the rate of change of internal energy is given by, so I'm assuming it's adiabatic. We're not bringing heat. I'm just raising the parcel. Then on the right-hand side, I only have the work done on the parcel, which is minus the work done by the parcel, obviously. And so it's minus p d alpha, specific volume. Okay, now we use the ideal gas law. P is rho RT that you saw this morning. And you can replace 1 over rho in here by its expression in terms of P. And then you get, as you did this morning, I'm going quickly because you saw this morning, but if you do you want me to do it on the board? No? You're good? If one person wants it, I'll do it. You're all happy? Okay. I never actually, we talked about this with David, and we thought that it was worth seeing twice because it's so important. So it is important. Okay, potential temperature is conserved, and that's an important result. Okay, so back to the math. So you have Cp d of log t is Rd of log p. And so you can combine those two expressions to show that T over P to the power R of Cp is constant. Okay, potential temperature is constant. And we'll see that it is sufficient to determine whether an atmosphere is, a dry atmosphere is stable or not. But before that, I promised I'd give you some hints on the, on the terms and when the approximations that we made here break down. So let me do a few remarks. And in fact, I kept adding those remarks as I was preparing the lecture notes, and I think they're actually quite interesting. So the first one, the ideal gas law. The ideal gas law, so given that you also the first law of thermodynamics, maybe you are all familiar with this. But just to comment, so usually when you see the ideal gas law, you have another expression. It's not P equals rho RT. This is an expression that we use in atmospheric sciences, not so much in physics. How did you see the ideal gas law? Something like this. Yeah? And so this is typically for a fixed, so we have again a volume of gas of a given pressure and temperature. And then N is, what is N? I usually like the molecular version. The moles are more useful in physics, but number of molecules. So this is the number of molecules. It's true, but it's just that there's a, if we see the molecular, the Muller, and then the specific versions, you're going to be all confused by the end of the day. So this is the number of molecules within the volume. And then in that case, K is the, Boltzmann constant, yes. So actually in the book by Bohren and Albrecht, they say that it's Boltzmann constant, but it was actually discovered by Planck. So I'm not sure, but I'll call it Boltzmann constant. Okay, that's usually how you see it, but in atmospheric science, we don't have such a thing as a volume, right? We don't have a volume outside. We can measure density much more easily. So we write this in terms of density, and I just want to go through the derivation of the expression in terms of density. Okay, so to get density, I have the number of molecules. I want the mass, so I need the molecular mass, call this M, and then I have to divide by M times T. So this is the density. So M is the molecular mass. You agree? If I multiply the number of molecules by the mass of each molecule, I get the total mass. Divide by the volume, I get density. And this is called the specific constant. Now you all know why specific, because it's per mass. We don't know why, but at least it's consistent. It's usually denoted R. And the point I want to emphasize is that K is a constant, a universal constant. I can give you its value. R is not. It depends on the gas that you have. And in fact, if it's a mixture of gas, you have the mean molecular mass at the bottom. The expression is not different. Okay, but here we have dry air. When we add moisture, that's going to change our ideal gas law because it's going to change R. And so we will have to specify whether we refer to R dry or to R water vapor. Okay, these are not the same thing because the molecular mass of water, of moist air, of water vapor, and of dry air is not the same. Okay, so one thing to keep in mind. Is that clear? Yeah, so the ideal gas law is universal in this form, but the way we changed it for atmospheric purposes, it's not universal anymore. Okay, the constant is not constant, which is annoying, but once you get used to it, it's going to be okay. We'll manage. Okay, another remark. Any question on this first? Okay, I just wanted to highlight this. Okay, another remark, something that was kind of discussed quickly this morning, but I think it's quite interesting. You saw that the heat capacity at constant pressure is the heat capacity at constant volume plus this specific constant. Okay, so this is the heat capacity specific. This is all per mass. In atmospheric science, it's always specific, or very, very often. Specific capacity at constant pressure. This is the specific heat capacity at constant volume. And do you remember, so this one we know which equation it satisfies, the first law. Tell me if I write too fast. I have a tendency to write fast. Okay? So this one we know it's related to the first law. And if, I'm going to even call the volume alpha. And indeed, what is if we're doing a transformation at constant volume, what is this term? 0. There's no change in volume by definition of our transformation. So you have CV dt equals Q. Okay, so at constant alpha, we have, and I'm going to write this as dt, this should be delta Q. It's an infinitesimal delta Q. Again, as mentioned earlier, this is all understood that these are changes very often with respect to time. Okay, but it could be actually more general. So the change in temperature is related to the change in to the heat added, which I can write dt is delta Q over CV. So what does that mean? What does CV mean physically? Let's say you have a volume and I add some heat here. If the heat capacity is very high, how will the temperature respond? Well, if the heat capacity is very high, then the temperature change is very small. Okay, so it's the name is heat capacity comes from the fact that it represents the capacity of your parcel to absorb heat without changing its temperature. Okay, so it's the capacity to absorb heat without changing temperature. So for instance, if I ask you what's the highest, the heat capacity of land or the heat capacity of the ocean? Specific. Yes, thank you. It's always specific here. Yeah, the heat capacity of the ocean is larger. If anyone has lived, you know, if you go on the, say, the maritime climate or more continental climate, you know that the variations in temperatures are much higher when you're in a continental climate. And that's simply because the heat capacity of land, the land is very silly. You heat it, it warms. You cool it, it cools. Okay. The ocean is a little more clever. If you heat it, it doesn't warm that much. It actually absorbs a lot of its heat without changing temperature. Okay, how about this one? And what I'm trying to get at is why is CP larger than CV? We'll try to understand physically where that comes from. So if you remember the equation that we had for this one, I guess we could derive it from there. Let's start from the first law. I could use it because you saw it this morning, but you only saw it this morning, so maybe it doesn't hurt to see it a second time. It's quick. So how do we derive the similar equation in terms of CP? Well, here, as you saw, P alpha is RT, right? So we're gonna write this as dq minus P, actually minus D of P alpha plus alpha dP. Yeah, I'm changing variables. Again, should use alpha here. Again, in thermodynamics, you always have the choice of your variables. You can pick two among those three. They're related by the ideal gas law. P alpha is RT. So they're related by the ideal gas law. So you can express everything in terms of PT if these are your favorite variables. Or you can decide to express in terms of alpha and T. Usually in atmospheric science, we pick pressure and temperature, usually. And so here, this is an expression in terms of temperature and density. For CP, it will be a similar expression in terms of temperature and pressure. Okay, and so we no, so P alpha is RT. So I have RT and CVT. CV plus R is CP, and so I get CP dt is delta Q plus alpha dP. I could box those actually. You never see those enough. Okay, now you see the similarity with the other equation. What happens if I heat a volume at constant pressure? This term drops, and so similarly we get that dt is delta Q over Cp. Okay, and again, Cp is the capacity to absorb heat at constant pressure without changing temperature. Yeah? Okay, so now why is Cp larger than Cv? Does it make sense? Let's try to do a thought experiment. And in thermodynamics, it's the first thing that you see when you open a thermodynamic book is a volume or a box with a piston, right? You'll always see a piston in thermodynamics. So we're going to do a thought experiment with a piston. And we're going to do two experiments. One at constant volume. I'm going to write constant volume. And here, at constant pressure. So what I'll do is I'm going to add heat to whatever molecules I have in those boxes, either at constant volume, so I'm holding the boundary fixed, or at constant pressure, hence the piston, and there's a little mass here. Why do I do that? Well, if this doesn't move, it means that the pressure is equal to the mass, the weight of the mass. So it's a way to get experiments at constant pressure. You put a little mass at the top of your box. And this boundary is free to move. Yeah? Does that make sense? Yeah? Okay, so let's add heat here. And then if you add heat, then the temperature will increase as expected, and delta T will be Q over Cv. Now I'm adding heat here. What do you think will happen intuitively? I'm not going to show it from, with equations, but intuitively, what do you think will happen if you add heat? Do you think that the boundary is going to move? Probably it's going to move up, right? So this thing will move up. That's what you would expect, and this is what will happen. And so if we compare delta T1, or delta T constant volume, if we compare this to delta T pressure, which one do you think warms the most? The first one, why? Exactly. Here you've done some, you haven't, the molecules have done some work to move the boundary. And so this will be smaller than delta TV. Some of the heat is lost as work to move the boundary, to move the top, I don't know how to call it, the top wall. So what does it mean in terms of heat capacity? Which one is more clever? This one, right? So we expect Cv to be larger than Cv, and this is what we saw. Yes? So here the collisions are the same, but there's no movement, right? And the work is related to a force times a velocity, and there's no movement here. Yeah? Here you've lost some work because you have moved the wall, the top. Yes, and so the temperature, the temperature is smaller. Yeah. Yeah. Any other question? You're happy with this? Yes. Yes. Actually, does anyone know that? What happens when you heat land compared to when you heat the ocean? Why can some molecules absorb heat without changing temperature? Where does the heat go? Yes, vibration. There's again a whole chapter on this in Bohren and Albrecht. So if you're interested, they should have the book here because they asked for a list of books. I put it in. So yes, it has other degrees of freedom to absorb that heat. That's why I say it's clever. Has other ways to absorb. I don't know if it's the term, but anyway, you see what I mean. Any other question? Yes. So for dry air, it's not constant. It depends on what you talk about. Definitely, yes. For dry air, they are constant, though. For dry air, we know the value, but they're not the same for other gases. Yes, they depend on the gas, on whatever actually. It does depend on temperature as well, but weakly. Yeah, we usually happily neglect it, especially in my part, because I try to give you the zeroth order picture, not to go into the details of the exact computations. If you want to have, I think the best reference to have all the thermodynamic equations, especially when you start adding moisture, things get really complicated. The exact derivations will be in Kerry Emmanuel's book. He's very careful at keeping all the dependencies on temperature and humidity. Yeah, most of us tend to be a little more approximate. Where does it come from, the temperature dependence? It's a good question. Mathematically, I know, but to give you a physical reason, I'm not sure. Does anyone have an idea? Mm-hmm. Yeah. Mm-hmm. You have discrete levels. Okay. So the answer is it's complicated, but you can ask Freddie about it. I'll refer to him. Okay. Another assumption which I've hidden in there is that the work, I've written the work of pressure forces as minus PdV. And actually the nice thing about atmospheric sciences is that the only work that we have to worry about most of the time is the work by pressure forces. So I've written that the work is minus P d volume, specific volume. How true is that? So here, I'm going to do another thought experiment. Okay, so I have a volume and I'm going to increase its volume. And so I move the piston slowly. Actually, when we write this, one of the assumptions that we have is that the pressure, if we go back to the parcel, oh, I wrote it actually. So this assumes that the pressure of the parcel is always in equilibrium with the environmental pressure. Okay? And it's not true of other fields, but the pressure does adjust very quickly. Okay, so when you raise your parcel, the pressure within the parcel will be at equilibrium with the environmental pressure. Now, in what case is that not true? Yeah, so you'd have so when you have a gradient of pressure, you have sound waves being generated. But so how fast do you have to move? Actually, I don't need my experiment. This would be sufficient. So let's take this parcel. And if I move it too fast, what's going to happen is that sorry, I have to think of the best way. I think the tank experiment, thought experiment might be easier. Okay, so I go back to my little tank, sorry. All right, so I move slowly the wall, And so if I move it slowly, the pressure will always be in equilibrium with whatever mass I have here. So I'm just removing mass slowly. So I'm doing m minus dm. I'm removing mass slowly, and so I'm assuming that the pressure of the gas molecules is always in equilibrium with the weight of the mass that's above. Now, it's not going to be true if I move the boundary so fast that the molecules don't have time to hit the wall. I don't know if that was very clear, so let me say that again. These are two experiments. This is the case where the work is minus p d alpha, and that's when I move this slowly enough that the pressure of the molecules hitting the wall is always in equilibrium with the mass above, the weight of the mass above. Now this is another experiment that you can actually do in a lab, where you move it almost instantaneously, and so the molecules don't have time to hit the boundary as it's moving. And eventually what you get, obviously, from now the second law, is that your molecules will then happily take all the volume. And so this is the initial state. This is the final. This is the initial state. I'm removing masses, and I get the same final state. It looks like, but actually it's not the same final state. If you do this, what do you think the temperature change will be? What is the work by pressure forces when I remove this wall instantaneously and let the gas expand within the volume? There's no work. It didn't do any work, it didn't heat anything. So how's the temperature here compared to here? Increase? Let's vote. Who thinks it has increased? You pull it, actually the way it was done in the lab, to be very precise. I forgot who did this, I should have checked. I'm sorry for, I'll find the name. He put a glass window here. Gay-Lussac, is it? Okay, thank you. So he put a Gay-Lussac put a glass window here, and a little ball, which was made of iron, held by a magnet. And then they released the force by the magnet. The ball fell, and the whole glass window broke almost instantaneously. And obviously the gas expanded. And then he went back and measured temperature. From the first law, we know that the temperature change, this is adiabatic, I'm not adding any heat. The temperature change is related to the work done. The work done is 0. So the temperature change is 0. And indeed, the temperature change from here to here is 0. And Gay-Lussac proved it. He measured and found the same temperature. So when we assume that the work is minus p d alpha, we assume that we're moving slower than molecules, basically. Okay? Something to keep in mind. So what's the speed of molecules? Do you know? Yeah, it's the order of speed of sound, so 300 meters per second or so. So you have to be pretty quick. That's why they used an iron ball, because it's kind of hard to move at 300 meters per second. You can try, but it's difficult. So as long as your updrafts are slower, than the molecule speed, you're fine. And for most atmospheric applications, you're fine. Okay, and one last remark. One last remark is that, so David mentioned this morning there's a whole zoo of energies that you've heard about. Kinetic energy, internal energy, now you all know where they come from. There's another one, dry-static energy, which you may have heard of. And I just want to show you here that it's very closely related to this potential temperature. And in fact, the potential temperature conservation is translated into dry static energy conservation if you have the hydrostatic approximation. Okay, so potential temperature conservation is always true, as long as you move slower than molecules, but it's always true. Now, if you make the approximation that your atmosphere is hydrostatic, then the dry static energy is conserved. Okay, let's Maybe let's show that. Okay, so we had that Cp. I'm just going to start from any convenient point. So from this point here, we had that Cp dt over dt minus r dp over p is equal to 0 in this it's called quasi-static. Did I say that? When you move, when the pressure is in equilibrium with the environment, so you move slow enough that the pressure is equilibrated. That's called quasi-static. And so this is 0 in our adiabatic quasi-static displacement. And so we do the hydrostatic approximation. dp dz is minus rho g. And so we get that Cp dt over t minus, so plus r dz rho g over p is equal to 0. And obviously we're going to use the ideal gas law, so we have P is rho RT, so I can cancel those. And I get that Cp dt plus G dz is equal to 0. And how do you call it? H. And so H, which is Cpt plus Gz, is constant. Okay, so once you have potential energy conservation, it's straightforward to get the dry static energy conservation under the hydrostatic approximation. So it's worth noting here. Okay, any question? That's quite straightforward. Okay, so that was a long detour, but I hope it was interesting. Let's go back to our original question that we had. Is the atmosphere stable or unstable? Now we know we have a conserved quantity, but how does that help us? Well, it does, because again, a lot of our trouble in atmospheric science comes from the fact that things depend on two variables. That's what makes our lives miserable or interesting. It depends on temperature and pressure, or temperature and density. But so here, because we have a conserved quantity, we can very easily see if an atmosphere is stable or unstable. So let's take our parcel, and I'm going to show you that the only thing you have to look at is whether theta increases with height or decreases with height. So let's suppose that we have a potential temperature profile like this, and the bar means the mean over some region. And you take a parcel near the surface and you raise it adiabatically. And then here, its potential temperature is conserved, right? We just showed that from the first law. But so what does that mean? Well, here, its potential temperature, I can decently compare to the potential temperature here. Or, it's actually scary. What's that? I think there is unstable atmosphere here. Theta increases with height. We are in that case. We haven't brought in moisture yet, so we're not exactly relevant to what's happening outside, but soon we will be. Okay, so I raise it here, and the thing is here, I can compare to the environment at the same level. They have the same pressure. So I'm getting rid of this problem that I have of depending on two variables. Now if I compare the temperature at the same pressure, now it does tell me something about density, right? And so here, this temperature, the potential temperature is lower, so the temperature is lower than the environment at same pressure, and so it's heavier. And so it goes back down, and that's a stable environment, stable profile. This is the neutral case, so it's conserved, it goes up, and here at the same pressure I compare with the environmental potential temperature, it's equal, it just stays there happily ever after. And here, this is the interesting case, the one that's going to convect. If you raise a parcel, here it's at the same pressure, its potential temperature is larger than the environment, hence its temperature is larger. And so it's lighter, it keeps rising. Okay, so if you want to know if an atmosphere is stable to dry convection, all you have to do is look at temperature, potential temperature. So if you go in the atmosphere and you measure a potential temperature profile, what do you think it looks like? Do you think it's stable, neutral, or unstable? Stable? Let's vote. Who thinks it's stable? Who thinks it's neutral? Who thinks it's unstable? Yeah? Some people don't think. It's very, very neutral. Okay, let's think about this. Why is that? It's very neutral. Notice that here I stop at 1 kilometer. We'll see why later. But why do you think I'd stop at 1? What? Yes, and what happens at the top of the boundary layer? What's that? You could have an inversion, but I was thinking what changes in the first law, for instance, in everything that we've done, what changes once you go higher in the atmosphere? I give you, yes, condensation, clouds. So half of the time when I ask a question, you can just say clouds, and it should be correct. Yes, you have clouds, and so when we did our displacement, we had an adiabatic displacement, so delta Q was 0, but now we'll have the latent heat. So we'll have the term that has to, that comes from the condensation. So I'm stopping at 800 meters, 1 kilometer, but it's very, very, it's very constant. And so why is that? Let's think about the mechanisms that tend to destabilize the atmosphere. So to make it unstable, you have to cool above, and that will happen if you have radiative cooling, right? If you have a parcel of air, it emits radiation, which depends on its temperature, its humidity content. And the cooling in the interior of the atmosphere tends to make the profile unstable, but this is quite slow. You also have surface warming that can lead to an unstable profile. And then what brings you back towards the neutral profile? Convection, yes. And convection is very fast and very efficient, right? So you've all put milk in your coffee cup and mixed with your spoon, and it's very efficient at mixing. Similarly, the convective rolls that we have in the boundary layer, they're very efficient at mixing. And they're quicker than the destabilizing effects. And the consequence is that as soon as this thing is trying to destabilize, it's brought back towards the neutral position by convection. Okay, a small thing I haven't told you. Here, it's not potential temperature, I'm cheating. It's virtual potential temperature. Do you know what that is? Yeah, it's to account for the fact that when we compared the temperature here, we assumed that the density was only a function of temperature and pressure. With moisture, you have to add a third variable, which is water vapor. And as usual, we try to go back to something that we know, and so we try to do as if there was no moisture, and it turns out you can. We'll go through the derivation of virtual temperature. So it's a temperature that dry air would have to have the same density as moist air. Okay, just without any latent heat, without any condensation, just the fact that you have H2O molecules in your volume will change your density. And you can just forget about H2O, assume it's all dry, but then you have to change the temperature a little bit, and it's called virtual potential temperature. We'll derive it soon, hopefully. Yeah. Yeah. Yeah, that's a good point. So actually, when I say it's very constant, during the day, you know, you have a lot of variation. At night, you have lots of radiative cooling, so it tends to cool the surface. During the day, it warms. Yeah, so near the ground, other things happen. That's true. It's a good remark. Yeah. Because that's where the dry convection is most relevant. If I look higher up, this is from a review by Bjorn Stevens, which, if you're interested in this topic, by the way, is very interesting. And see, at the top of the boundary layer, you have latent heat release, and that changes the thermodynamics. So we're going to have to change the equations once we reach those altitudes. So for now, we're limited to places where we can have water vapor. This is the virtual effect. But they're not allowed to condense into liquid or ice. And here where the virtual temperature, but the point is that everything is well mixed actually, so it's all very, convection is very efficient at mixing and bringing you back towards the neutral profile. That's the bottom line. Yeah. You mean in oceanography? So yeah, so in the atmosphere, the density decreases roughly exponentially, right? So the change in pressure decreases exponentially. So the change in pressure is very strong. In the ocean, indeed, the density changes are very small compared to the mean density, but like 10. You have 1,000. Trying to, yeah, it's probably like 10% at most, probably a few percent. Yeah, oceanographers in the room, you agree? A few percent. Yeah, so it's much less of a problem than here, indeed. But you do have, but there is potential temperature. Yeah, yeah, there is. Yeah, 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 yeah. Yes, so you have a different equation of state. You have a different equation of state in the ocean. Yes, yeah, you can still. It's much more complicated, and it's still, I think, debated, in fact. Or, but yeah, the equation of state in the ocean is not as nice as the one we have in the atmosphere. Um, okay, and here, so when you Google potential temperature, it's usually our well mixed layers. It's usually associated with pollution, and the reason is someone mentioned inversion. And inversion is a case where the temperature increases or is very does not the potential temperature increases above your boundary layer. And so what happens is that convection has a really hard time piercing through this stable layer. Sometimes it's just a thin layer. And so whatever pollution you're releasing in your mixed layer, it's well mixed here. And because you have a stable, we saw that if theta increases, it's stable. And because you have a stable layer above, nothing pierces through. And so that's really bad for pollutants. They tend to stay there for a long time. And here it's really striking. You do see the inversion very, very clearly. The plume is rising, and then it's completely stopped on its way because you have very stable air above. Whatever it's trying to do, it's not going to be lighter than what's above. Okay, and so another note in passing, it's a low-hanging fruit, just like dry static energy. It's very easy to derive the dry adiabatic lapse rate. David will do that too, so I'll go quickly. So from the conservation of the dry static energy, it's very straightforward to get the dry adiabatic lapse rate. So the lapse rate, the temperature decrease expected in a dry atmosphere. And it's just minus G over Cp, so about 10 degrees per kilometers. Right, going fast, is that okay? Yeah. Okay, but as we've now mentioned a couple times, I'm stopping at 1 kilometer because above that you have phase change, latent heat released, and things get a lot more complicated. And so, as much as I like dry convection, I think it's time to turn to moist convection. And I'll start by introducing some of the variables that we need. This is not exhaustive, by the way. Okay, so maybe I'll slow down a little bit because I don't know how new this is to some of you. And I also have some questions just to get you familiarized with those notions. So in fact, I'm asking you to derive the virtual temperature. We'll do that. And again, so as soon as you see moisture, try to go back to the dry case. So trying to find a trick so that you land back on your feet, something that looks like the dry case. So the goal would be to try to have something that looks like the ideal gas law. Okay, and we'll manage introducing the virtual temperature. We want to find something that's conserved, like potential temperature. And lucky us, there is something, equivalent potential temperature, which is approximately conserved. Okay, so we'll have to do some approximations. There's a trade-off, but what we win is enormous because we go back to the dry case, which we know much better, which is easier to deal with. Okay, moisture variables. So, first of all, okay, the density. So from now on, we're going to have a lot of subscripts. The density of water vapor, so it's the mass of water vapor in whatever volume you have, call it V, I guess. And the dry density is the mass of dry air divided by your volume, so that the total density is the total mass over V. I should take notations. I have, as usual, our favorite parcel V with the total mass in it, composed of dry air and water vapor. Okay, but this is usually not how we measure water vapor. We like, if you haven't noticed, we like specific quantities, which mean per unit mass. And so typically we use the specific humidity, which is the density of water vapor divided by the total density. Okay, and if you compute this, the volume goes away, and you just have the mass of water vapor divided by the total mass. The specific humidity. And sometimes we also use the mixing ratio, so I'll mention it, though I'll mainly be using the specific humidity. So the mixing ratio is the ratio between the amount of water vapor compared to the amount of dry air. Okay, so that's for measures of water vapor amounts. Now in terms of pressure, so we have to deal with two pressures. The partial pressure of water vapor, which, now if you remember, the specific constant is K over the molecular mass, which is not the same for water vapor and for dry air. So I have to specify that this is the constant for the water vapor, and it's the partial pressure of water vapor. P sub D is rho D or dt, partial pressure of dry air. But again, the nice thing is that actually we can deal with the total pressure, and we can express it in terms of those two pressures. And it's even nicer because it's a very simple relationship. It's the sum of those two. This has a name. Do you know the name? It's probably written. Dalton's law. I didn't mention also the fact that the internal energy, this is a side note for famous people, CV dt, that the internal energy is equal to CVT. That has a name as well. Some other scientist. Do you know? Anyone? No? Joule's law. Okay, that was a side note. Okay, I don't care if you forget the names. I would care if you forgot what it means or how to write the equation. Okay, so Dalton's law is helpful because we have a relationship between the total pressure, and it's very simple. It's just the sum of the two partial pressures. Then a useful quantity is the dew point temperature. I think you all know what that is. If you have a parcel of air, it's the temperature to which you have to cool it. So we haven't seen actually how condensation occurs, and we'll see that soon. But basically, to get condensation, it's favored at colder temperatures. Okay, and so here, if you have a parcel with a certain amount of water vapor at a temperature T, you have to cool it to reach the condensation point. Sorry, I'm here. And then this colder temperature at which it starts to condense is called the dew point temperature. probably all heard that, so I'm not going to write this. The virtual temperature is perhaps a little more new. TV, virtual temperature. And again, so it's the temperature that dry air would have to have the same density as moist air. So temperature of dry air with same density as moist air with the same pressure. Okay. So here I want to stop and ask you a few questions, because that was maybe a little overwhelming, lots of notations. But first a question, what do you think, is moist air lighter or heavier than dry air? Heavier? I'm going to take votes. Okay. So again, I'm going to take our favorite volume, dry, moist, certain pressure, volume, temperature, same pressure, volume, temperature. The difference is that here I only have N2, O2, and here I have some dry molecules, but also H2O. Which one is heavier? So who thinks the dry air is heavier? Okay. Who thinks the moist air is heavier? More and more people not thinking. I don't know if I should worry. Okay, so the first thing that I probably would have thought is if you have water vapor molecules, you're adding molecules, so it's heavier, right? But there's a problem with this thinking. Why? Yes, the ideal gas law. One of the consequences of the ideal gas law is that N, so you have PV equals NKT. So the number of molecules here is the same as the number of molecules here. So you're not adding water vapor molecules. You're replacing dry molecules with moist molecules. Whatever that means, or O2 and N2 molecules with H2O molecules. Right? So now let's think of the molecular mass of those things. What's the molecular mass of N2 compared to H, say? So N is 14, so that's 28. How about O2? What is O? 16, 32. And how about H2O? 18 mH. It's lighter. Moist air is lighter than dry air. Okay, another question now. So, this being said, should the virtual temperature be warmer or colder than temperature? Okay, so what is virtual temperature again? Remember, it's the temperature that dry air would have, that this dry air should have to have the same density as this guy, or the same mass for a fixed volume, say. Okay, so here I want the same mass. We know this one is lighter. Okay? So to have the same mass here, do I have to make it warmer or colder? Okay, I want to make it lighter. If I make it colder, I'm going to make it heavier. You're going to be grilled, but yeah. So here, if I want to make it lighter, I'm going to have to increase its temperature. Do you agree? Yeah. So TV has to be larger than T. Okay. Shall we check? Okay. Let's derive the expression for TV. Do you want to do it, or we can? I have it in the slide. We can do it. I'm happy to do it, or we can move to the rest if you're comfortable with this. Should we do it? Yeah? Maybe let's do it. Okay. It's a lot of notations, but you get used to it. Okay, so virtual temperature. Actually, I'm going to erase everything. I don't need this anymore. Okay, so I need some notations. Gonna have some. I don't know why I erased because I'm just writing the same thing. Then I have rho V, rho D. Okay. Okay, and so P. Okay, I want the equation that governs the virtual temperature. So it's the temperature that dry air would have to have the same density as this parcel. Okay, so with the same temperature. So I know the density is the same. So TV, temperature of dry air with same density and pressure as the moist air that I drew there. Okay, they have the same pressure, the same density. So I'm trying to get an equation for the virtual temperature. So something like this. Now, which constant should I use here? Dry. Okay, this is the equation of dry air that has density rho, pressure P, and virtual temperature TV. Do you agree? Yes, this is for dry air, so we're good. Okay, we have an equation. We're finished now. We're good. So, and now I just have to use Dalton's law. So this is rho V RV T plus rho D RD T. Okay, and we're going to be able to express TV in terms of temperature, RV, rho V, rho D, etc. Very good now. This was the hard part. Does that make sense for everyone? Yeah? If your conceptual parcel of air, dry air, has the same pressure and density and virtual temperature TV, it has to satisfy this ideal gas law. Here? No. What I'm saying is that here, I'm imagining a parcel that has the same density as this guy. And the density of this guy, rho, is the sum of both. So rho is the sum of both. Okay? Okay, so here we can deduce TV, which is T times, so we have rho V RV over rho RD plus rho D RD over rho RD, and that's it. And I want to use, I'm going to express everything in terms of specific humidity. So I don't really like rho D. I'm going to write it as rho minus rho V. Over rho. Okay, just got rid of our rho D to make those moisture variables appear. Okay, so what is this? Rho V over rho. That's the mass of water vapor divided by the total mass. That's a specific something, it's per mass. And then it's water vapor, so it's specific humidity, QV. Now RV, I'll keep it like this, RV over RD. Oh, I give it here. So we have a notation, but I've added so many notations that I feel bad giving you yet another one. But there's something we call epsilon, which is RD over RV. Okay, but I'll keep it like this for now. We'll go back to this later. Let me spare you a little bit. And then we have 1 minus QV. Okay, so the virtual temperature is T times 1 plus QV times RV over RD minus 1. Okay, and now I'm going to maybe introduce this. So it's the temperature times 1 plus QV times 1 over epsilon minus 1. Okay, so let's check whether that makes sense. Okay, first of all, if QV is 0, there's no water vapor. The virtual temperature is equal to the temperature. That's good. Then we said TV should be warmer, so we have to figure out what this epsilon is. Okay, so I mentioned epsilon is RD over RV. If you remember where this R came from, what was its expression? K over the molecular mass. So we have K over the mass dry divided by K over the mass water vapor. And so it's mv over md. And in fact, I don't know if that bothers you, but my students often complain that when you introduce an epsilon, you tend to put your perturbation over your reference. And so they complain that it's dry over vapor when you really want vapor over dry. But that's just because really it should be vapor molecular mass divided by dry molecular mass. So it makes more sense to express it in terms of molecular masses. It's a good way to remember what its expression is as well. Okay, and we don't care what its value is, we just have to figure out whether it's smaller or greater than 1. But we just said that. What is it? Is it smaller or greater? Smaller, right? We just said that H2O is lighter than dry air molecules. So epsilon is smaller than 1. And so it's actually 0.622, I believe. Should have the value somewhere here. You see it? Oh yeah, 0.622. And so it's more than 1, and so 1 over epsilon minus 1 is positive, so TV is larger than T. And notice how everything fits together. If QV is 0, you recover your usual temperature. There's no virtual effect. That's consistent. But also, the fact that TV is warmer is related to the fact that the molecular mass of water vapor is smaller than the molecular mass of dry air, which was our physical intuition behind it. So it all makes sense. Okay, so far so good. I think I have 5 minutes left, so maybe I'll just start talking about condensation and we'll finish on the moist convection next time. Yes? That's a good question. So, so here, you have to remember what we care about. What we care about is the density in fine. And the reason why potential temperature was interesting is because it allowed us to compare something here with something here at the same pressure. And this something was so the temperature basically, because the pressure is the same. So if potential temperature, if you compare the potential temperatures, you're essentially comparing the temperatures. Pressure is the same, it's just a factor in the potential temperature. But you want something that tells you something about density. Temperature does not. Virtual temperature does. Okay, so it's all a matter of what we want is rho, but what we have is temperature and pressure. Okay, and so if I just compare potential temperature, I'm comparing the temperature of this guy here with the temperature of this guy here at the same pressure. but they don't necessarily have the same humidity. So it's really the virtual, to account for this virtual effect. I should say this is quite small, actually. And you see QV, oh, I should have told you, what's the order? David will talk about the distribution, so he'll cover this. But what's the order of magnitude of QV? Yeah, 10 to the minus 3, a few grams per kilogram. So it's quite small, 10 to the minus 3 times something which is smaller than 1. That's something small. So it tends to be a small correction, but QV is small, but then the when it's important. Not so much for the virtual effect. I mean, near the ground you can have some differences because there's most of the moisture, most of the water vapor is concentrated near the ground. Decays roughly exponentially. But as soon as you're above, say, the first, I don't know, a few hundred meters, then you don't have to worry about virtual effects. They're fairly negligible. So that makes sense why virtual temperature matters. Really what we want is density, but we don't have it, so we're trying to find clever ways around it. Okay, so maybe it doesn't make sense to start on condensation now, because I think I have 2 minutes. So maybe that's how far we can go without talking about phase change. So I'll add another layer of complexity next time. I should stop here. Thank you. Oh yeah, and so the people who volunteered for the lecture notes, if you could